Hey everyone, welcome back to my YouTube channel. You are watching Build AI with Sandeep. So today we are going to continue our uh, LLM series that how failures build modern AI. And we are going to discuss about the second fix that researchers did in activation functions. So we are going to discuss that fix and let's start the today's video. So firstly, I want to discuss with you that what are activation functions. So these are the functions that used in neural networks that decide whether a neuron should activate or not. If you didn't understand, then don't worry. Let me explain you in simple way. That activation function takes an input and convert it into another output that can be the input of the next layer. So without activation functions, neural network are simply just doing the linear operations, nothing else. There is no learning without activation function. So the second thing is why activation functions. So there are three major reasons that we use activation function in neural network. The first one is to introduce non-linearity. So what is non-linearity? It means that there is no straight line relationship. For example, let me make you understand by a simple example that, for example, y equal to x. So if x is equal to 2, then y is equal to 4. If we double down the x, then x equal 4, then y is equal to 8. So there is a straight line relationship. This is x and this is y. There is a straight line relationship. But what if y is equal to x here? Then in this case, if we double down the x, then y will not get double. So for example, if x is equal to 4, then 16. So y did not double, gets double. So that is called non-linear relationship. If there is no straight line relationship, then the function is no non-linear, or we can say in real world data does not follow linearity. They are non-linear in nature. So we have to introduce non-linearity in our neural network. That the second reason we use activation function is to learn complex patterns. Since we know that real world data is non-linear and our neural network should be capable of capturing multiple non-linear relationships. So non-linear relationships are like curves, boundaries, and complex patterns that are present in image, text, speech. So our activation functions should capable of capturing these complex patterns. That's why we use these activation functions in our neural network. The third reason is to control output range. So let's suppose, so this point is very important. We know there are two main problems in training of neural networks. The first one is vanishing gradient problem. The second one is exploding gradient problem. So vanishing gradient problem arises when the output is too low. So let's suppose too low. So this small value, since we know that in back propagation there are differentiation, so multiple derivatives multiply with each other. So if one derivative is very low, then it multiply with another very low value. So that create the vanishing gradient problem. Our model neurons switch off and not learning at all. So that's why we need a function that control the output range. Okay, so these are the three main reasons why we are using activation functions in our neural network, or transformer based model are also a kind of neural network, a deep network. So now let's see what are the different types of activation function present. There are lot more activation functions also, but I right now I took important ones. So the first two are the basic one that was very Sigmoid and Tanh activation function, and these two was very popular in the early stages of deep learning. And after that, There are ReLU came into picture, Leaky ReLU came into picture, and for today's video, that the agenda of today's video is to understand that how researchers were able to train more than 12 layer transformer based language models. So GELU and Swiss are the two activation functions that help in doing this task. So let's understand each activation function one by one. So now, first let's understand what is sigmoid activation function. So first let me write the formula of sigmoid. Sigmoid is basically, so this is the formula of sigmoid activation function, and the graph of activation functions you can see on my screen that it ranges from 0 to 1, and sigmoid activation function, it is really good for probability, and we mostly use this activation function in binary classification problems when the target only has two values, two labels. So in binary classification problem, we mostly use sigmoid activation function, but there are some limitations of sigmoid activation function. The first one is again vanishing gradient problem. Gradient becomes very small and it multiplied with another small values that gives us very small value, and this creates vanishing gradient problems. Neurons does not able to learn properly, and it is not zero centered. There is slow learning. I will tell you what is the problem when the activation function is not zero centered in 10H. Just give me some moment, and it creates slow learning. And the third limitation was saturation. So let's understand the saturation point, that when the input, when the X is very high or very low, then there is no learning. Why? Because let's suppose X is 10, then sigma is 0.99 something. When X is 20, then sigma is more closer to 1, approximately 1. So in very big values, the output of sigmoid is 1 for each bigger value. So that it means that our input, our output reaches the saturation point. It is not increasing at all when the input is increasing. Okay. So similar case arises when the X becomes very negative, very low value. For example, let's say minus 20. So in that case also, it gives 0. It gives value closer to 0. In this case also, there is no learning. So this is the concept of saturation. And in graph, we can easily see that the maximum value is 1 and the lowest value of the sigmoid function is 0. That's why we only use sigmoid activation function in case of binary classification. Other than that, we move to next activation function. So next activation function is Tanh. Let me write the formula of Tanh. So this is the formula of Tanh. So Tanh solved the problem, one problem that sigmoid was not zero centered. So it is slightly better than sigmoid activation function because it is zero centered. So now let me explain the concept of zero centered, that sigmoid is not zero centered, so its output always positive, whatever be the input, it gives us a positive value. That means there is no negative value, there is no balanced updates. So that creates very slow learning, and apart from that, gradient moves in the same direction because all the outputs of sigmoid is positive. So that's why activation function must be zero centered, so that the activation function gives us positive, zero, negative values that allows the training, that allows the updates are stable during training. So Tanh ranges from -1 to 1. It is better than sigmoid because it is zero centered, and you can see the graph of Tanh, but it still has vanishing gradient problem, and it also has the same problem the saturate at extremes. So again, for very high value, it gives us output closer to 1. For very negative value, for very low value, it gives us the value closer to -1. It saturates at extremes. So that is the main problem. So there are two limitations in 10H also. So then after around 2014, ReLU came into picture. So ReLU was very powerful till 2018, and it is very simple and very fast activation function. It solved the problem of vanishing gradient problem for positive values. Just understand this point that it solved the vanishing gradient problem for positive values, and uh, its formula is max of 0 and x. So this is the formula, and you can see the graph is very simple. For all the negative values, it returns 0, and for all the positive values, it gives us the max of 0 and x. It means x value. So it worked great in deep networks. It solved the problem of vanishing gradient problem for positive values at least, but still it has a problem, and the problem was time value problem. Whenever neuron gets an input in negative, it gives us the output 0 and it stops learning forever. That is called time value problem. I already showed you in my previous video that this is a neural network. Let's take a simple network. So if this neuron gets negative value, then it stops learning forever. It becomes dead. That is called time value problem. There is information loss. So that was the biggest failure, and transformer architecture used the ReLU activation function. That's why the researchers faced the vanishing gradient problem during training of more than 12 layers transformer based language model. After that, Leaky ReLU came into picture to solve the ReLU problem, and it basically fixes the dying ReLU problem. That whatever be the value, leaky ReLU does not give you the 0 value. The neuron, it will not make neuron dead. So fixes dying ReLU problem, allows small gradient in negative region, and its formula is basically max of 0.1 into x and x. So researchers multiply rather than giving 0. The formula is basically max of 0.1 x. So this is the formula of leaky ReLU. Value does not become 0 anytime. At 0 it is 0, but otherwise for all the negative values it multiply with some small value so that it can give some output. But this also has the limitation that the 0.1 is fixed. It is not a static. It is not a constant given by theory. It is just a chosen constant. So for researchers experimented with different constants, 0.01, it could be anything, 0.1, 0.2, 0.02, 0.01, anything, and different data sets behave differently for different chosen constants. So that is the big problem in leaky ReLU, that the constant is not learned by the model, it is static and it could be anything. So that is the bigger problem that leaky ReLU also faced, and it is not also always optimal activation function. So before 2018, ReLU was the most powerful activation functions we were using. And to solve the time ReLU problem, to solve the ReLU problem, to solve our problem of vanishing gradient problem in language models, GELU came into picture in 2018. This almost solved our vanishing gradient problem, and it makes the training happen successfully for more than 12 layer language model. So what GELU did? What GELU changes fundamentally? So it reduce. So basically ReLU blocks everything negative. Whenever ReLU gets the negative value, it becomes 0, but GELU does not do that. ReLU actually makes the value smoother, reduce it smoothly. For negative value, for large negative values, it reduce it smoothly. It is not like every time it is giving zero for each negative value. So gradient never becomes exactly zero. In ReLU, gradient is zero dead zone, but in GELU, gradient is small but continuous. And it is a smooth function, stable optimization. So ReLU have two problems. First one is for negative values it gives zero, and the second problem is has it has a sharp code. But GELU also solve the second problem also. GELU is smooth everywhere, whether it is zero or whether it is any value, positive or negative. It is giving smooth optimization, less sudden gradient changes, better convergence in deep networks. So it has probabilistic behavior. Core intuition is like how important is this input? If the input is very large, very important, then value fully pass that value. If it is small importance, it has small importance, then it will partially pass. If it is not so much important, then it softly reduce the gradient. And the formula of GELU is basically, let me write here x, y, x. We are not going into the formula because when coding, we just need to write one line of code. We are the agenda of this video is not to go into much mathematical functions. GELU has very complex mathematical formula, so we are not going to touch it. But we understand that the main thing to understand in GELU is that to understand this curve, that why GELU came into picture, what problem it is solving. These two things we need to understand. And now let's move to our final activation function that we are discussing today, that is Swish or GELU. It is also came around 2018s and it also solving the problem of value that gives negative value, that gives zero gradient, dying neuron, information loss in deep networks. Swiss also fixes this by allowing small negative outputs, keeping gradient non-zero, smooth transitions. And Swiss formula is very simple, that it is x divided by sigmoid of x. And I already told you the sigmoid formula, that is sigmoid formula. So this is the formula of very basic formula, regardless of value activation function. And we know that if x is larger than sigmoid gives us value closer to 1 and output is x passed through. If x is near 0, then partially pass. If x is negative, then not killed but just scaled down. And this is the graph of sigmoid GELU activation function, and it is similar to the GELU activation function. So this also helped us to train the transformer based model, but GELU was slightly better than GELU because it plays smartly. Okay, and now we are wrapping up this video. So that's it for today. Now you clearly understand why activation functions are not just formula, but the core reason deep learning actually works. So the key takeaways are better activation function, better gradient flow, deeper and more powerful models. If you found this helpful, make sure to like, subscribe, and share this video to your AI friends, because next we will go even more deeper into how transformers actually learn. So see you in my next video. Thank you so much for watching.